The Fun with Haxl section. This is going to be a different Haxl talk from the one that you may have seen before. I've been giving the same talk for about 2 years. I decided it was time to do something a little bit different. So Haxl is a library that we designed to solve a particular problem at Facebook. And it does very well. It solves that problem very nicely. But it's actually more general than that. And I'd like to explore some of the things that you can do with Haxl in this talk. So I should mention that I like writing code a lot. I don't like writing slides so much. So I've written lots of code and not so many slides. So I'm going to be doing some of the talk in Emacs and some of the talk in GACI and demonstrating a few things. So what is Haxl? Well, this is where we started with Haxl. Haxl is a library for batching and parallelizing remote data fetching. But then we realized it just doesn't really capture everything. You actually want to do more than just data fetching. We'd like to be able to parallelize other kinds of remote data operations. So perhaps more correctly, it's for parallelizing remote data operations in general. But this doesn't really capture everything either. You might be doing things that are not remote data operations. It's for parallelizing other things too. So we can actually parallelize general I/O. But then the library does more than that as well. It actually caches things too, so we can say it's also for caching I/O, and it does memoization as well, so it's for memoizing I/O too. But we could go on like this for a long time. Maybe we should just say that Haxl is made of unicorns and rainbows and just be done with it. Which is kind of surprising because, to a first approximation, Haxl is a library with just one user, as far as I can tell, us at Facebook. It's actually been implemented in other languages more often than it's been used in Haskell projects. There's an implementation of Haxl in Scala and one in Clojure. So I'm looking for more users. Maybe I'll get some today, hopefully. So Haxl is open source. You can find it on GitHub. You can find it on Hackage. At Facebook, we're using Haxl in a major system that powers part of our anti-abuse infrastructure. So it's being used actively, heavily in production, serving 1 million requests a second globally. We've got dozens of engineers at Facebook using Haxl right now. So this is the only thing I'm going to say about how much we're using it at Facebook today. So let's have an example. Let's start with an example. So suppose you're making a blog, and you want to store the data for your blog somewhere. So you store the data for your blog in an SQL database. And we want to make a Haskell API for accessing that data. So I'm going to do this first of all without Haxl, and then show you what it's like with Haxl. So we need a monad for our blog. So this is going to be the blog type, and it's a reader monad. And in the reader monad, we're going to pass around a handle to our database. So then to run a blog computation, this is the run operation. So first of all, we'll open a connection to our database, and then we'll run in the reader monad blog computation, passing it the database. So let me just show you the database very quickly. So we've got some tables in our database. We've got post content, post info, and post views. And we can have a look at the schema for post info. So the post info table has, can you all see this? Let me see if I can do that. So is that better? Okay, so in the post info table, we've got a post ID for each post in our blog, a date, and a topic. So mostly going to be concerned with the post ID. And let's have a look at the post content table. So the post content table has a post ID for each post ID and the content for that post. So then we can do something like have a look at what's in the post info table. And you can see we've got 12 posts with different dates and topics. And we've got some content for each of those posts. So let's make a little Haskell API for accessing this. So we've got our monad. We'll just have some simple types for post ID and post content, and a couple of operations. One that corresponds to getting all the post IDs for all the posts in the database, and one for getting a single content for a single post. So given a post ID, it's a blog operation that returns the post content. So then the implementation is fairly straightforward. We'll have an SQL operation which takes a string, which is the query, and in the blog monad it returns, well, this is what an SQL query returns using this SQL library I'm using. It's either an error or it's a list of rows. And then we can just implement these operations using SQL. So get post IDs calls SQL, passing it the query, and then we just have to take the result and figure out what to do with it. If it was correct, then we just take all the ints and we return a list of ints. Otherwise, figure out what to do and throw some exception as an error. Okay, so that's fairly straightforward. Let's see if we can run it. So we can run. That gets all the post IDs. And if we plumb the output of get post IDs into get post content, mapm get post content, we get the post content for each of those post IDs. So the result is all of the contents of all the posts. And you can see that, so each time we did a select query, it printed it out. So the first time we printed out select post ID from post info, and then we have a sequence of queries for each of the post content. So that's the non-Haxl way of doing it. Okay, but there's one problem with this. So the problem is that we did multiple queries for each of those post contents. Every time we wanted the content of a post, we had to make a separate query for it. What we really want to do is to make a single query. You want to reduce the number of queries you're making to the database because a query is really expensive. It might be on the network, it might be a big database. So if you're selecting multiple things from the same table, what you should really do is just make a single select query. So how could we do that with our API? Well, you could make a multi-get post content API specifically for this kind of problem. And it would take multiple IDs and it would return multiple post contents. But this isn't really good. This is kind of a horrible way to do it because it's a special case of mapm. Right, so we're duplicating a concept that's already available as mapm. So someone using mapm somewhere in the code base might not realize, somebody might not realize you have this API. They'll go and use mapm instead and not benefit from the optimization. And what's worse is that it's sort of anti-modular. If you wanted to fetch post contents in multiple places in your code base, you have to sort of somehow connect them together and make a single multi-get post content call. So it means you have to restructure your code in ways that you probably don't want to do. So Haxl solves this problem. And I'll show you what it's like with Haxl. So let's load the Haxl version of the blog instead. So again, we can do get post IDs, and that gets all our post IDs. And let's do the problematic query again. And you can see this time, even though I used just the standard mapm, we've ended up making a single select query where post ID is in, well, here's the list of post IDs we wanted. and it returns all the post content as before. So the API is exactly the same. The monad is different. I'll show you what the monad is. But there's sort of magic going on behind the scenes to batch all those things together and make a single query. So let me tell you a bit about what Haxl is, what the API is. So Haxl is a monad. It's actually generalized, so there's a gen Haxl type, and it has an extra type variable. A is the result type as usual. This U type variable is just some data that you can pass around. So you can decide what data you want to pass around. It's a bit like having a reader monad on top of the Haxl monad, but we've sort of built it in so that you can just pass your own user data around. So we're just going to fill this in with unit most of the time and not use that. So there's one really important operation in the Haxl monad, and it's called data fetch. So data fetch is the way that you take a request, pass it to the framework, and the framework will manage fetching the result of that request and giving you back the data. So data fetch is generalized over the types of requests. So here's the request type that you're passing to data fetch, and it's a type constructor. We've used the type variable R for that, and it's parameterized by the result. So A is the result type, and you can see that it returns in the gen Haxl monad the same result type. And then there are a couple of constraints, and these things are used to tell the framework how to fetch the data for your request. So you can use the Haxl monad with any number of your own data sources, and for each of these user-supplied data sources, you have to define some things. You have to define a data type of requests and an instance of the data source class. And I'll show you how to do that. So here's an example for our blog of the kind of request data type that you would have to define. So it's a GADT. I've called it blog request, and blog request is parameterized by the type of the result. And each of the different requests in this type returns a different result. So in the case of fetching the posts, which corresponds to get post IDs, we're returning a list of post ID. And for fetch post content, which takes a post ID as an argument, it returns the post content as an argument. So this is quite common when you're making a data source. You have multiple different requests, and each of those requests has a different result type. So making a GADT sort of maps very nicely to that style. Okay, so going back to data fetch, we have to satisfy these two constraints, data source and request. So request, it turns out, is just boilerplate. So in fact, it's a type synonym or a constraint synonym for this set of requests here. You can have, you need to have equality, you need to have hashable, typable, show, and so on. So this is using the constraint kinds extension. Isn't it great that you can do this? It's really nice. So the reason that requests have to have all of these instances is because they're stored in a cache internally in Haxl. And I'll come on to that a bit later. So that's the request constraint that we need to satisfy. What about the data source constraint? So data source is a type class defined like this. It has a single method, and it has a few superclasses that you have to satisfy as well. So data source name is just a class that lets you get the name of a data source given the request type. So that's very simple. I haven't described it here. State key. Every data source needs to have some state. So in the case of our blog, we were passing around the handle to the database. And most data sources will need to have some state of some kind. So state key is actually a class with an associated data type. And that's what gives us this state parameterized by the request type here. Show one, that's just a show method, but what I really wanted to do was to write for all a show rec of A here, but you couldn't do that at the time. I'm not sure if you can do it now, but you. So we made this show one class that does that. Sorry, excuse me. It's going to keep going off if I don't shut it off. So there's a couple more arguments. Let's see. This is the fetch method. So the point of the fetch method is that this tells the framework how to fetch data for your particular request type, for your data source. So fetch is going to be executed by the framework, and it's going to be passed a list of blocked fetches. So I'll describe what the blocked fetch type is in a minute. So we have some other arguments. We've got the state of the data source, some flags, the user data, and it returns a perform fetch. So there are a couple of different ways that you can fetch the data. You can either fetch it synchronously, so this is perform fetch down here. If you fetch it synchronously, you just pass an IO action. The IO action fetches the data, and it will fill in some variables in here that I'll mention in a minute. You can also do asynchronous fetching, which I won't describe today. So what's the blocked fetch type? So a blocked fetch represents a single request that's waiting for a result. So blocked fetch is actually an existential data type. So this takes the type variable here represents the result of the request. So blocked fetch contains a request parameterized by some result, and there's a result var here that you can put the result into. And the reason this is qualified here is because we might have blocked fetches for different result types within that list. So, was there a question? So remember that we've got different request types with different result types. So this list here might contain requests with different results. So that's why we have to make an existential here and hide the type variable inside the data type. Okay, and what's this result var thing? So result var is it's an opaque data type with a couple of operations, put success and put failure. So the job of the data source is for each of these blocked fetch things to call either put success or put failure, depending on whether we got a result or we didn't, or we got an exception of some kind. So put success takes a result var, takes the result, and it's just an IO action. And put failure takes the result var, some exception type, which has to be a member of the exception class, and again, it just writes the result into that variable. Okay, make sense? Feel free to ask questions if you have any. Okay, so what about the state? I mentioned that we have to pass state around to the data source. So there's this class called state key, and the state key is parameterized by our request type constructor, and it has an associated data type. So for your data source, you can just instantiate this class with an instance of this data type with the constructor and the contents, which will be the state that you want to pass around and have available when you're processing requests for your data source. Okay, so this means that the framework is going to have to somehow keep track of, for each request type, a different type of state. So this means internally we're going to have some kind of mapping from type reps to state requests. It's not something you can do with an ordinary map, so we've had to sort of build a special purpose map inside the framework that lets us handle different values for a given key. Okay, so just sort of summarize what you have to do for a data source. You need a request GADT. You need some instances of things like show and hashable and so forth. You need an instance of this state key for your data source state. It can be empty, of course. Not all data sources have state. And you need an instance of data source which defines fetch, which describes how to fetch the data for your requests. And so the key point, just sort of reiterate this. The key point is that fetch is passed multiple requests at the same time. So that's how you can collect your requests together and issue a single select query if you're doing a database query, overlap things if you want to, and that's how we get concurrency. All right, so let's have a look at our blog data source. So blog data source is a module with some exports and some imports. And here's a couple of types, same types as before. Here's our blog request GADT that we've seen before. Here are our boilerplate instances. So we've got show untypable, show one, eq, hashable. Unfortunately for GADTs, you can't derive hashable or use the generic derivation mechanism, because that doesn't work for GADTs. So we just define that ourselves. So now we can define our request API. So this is just defined in terms of the data fetch operation. And data fetch, remember, takes a request. So here it's taking fetch posts for our request type, and that gives us the get post IDs operation. And get post content, again, we just pass fetch post content as a request. So here's our state. We have to make an instance of state key, and the state parameterized by blog request is defined as, this is the constructor, and the contents is the handle to our database. So we need an operation to initialize the data source. And typically this is done by returning a value of type state parameterized by your request type. And this is, in our case, just defined as blog data state applied to, we have to open a connection to our database, and that's the state. This is data source name. And to define fetch, well, we got our state, which contains the database handle. And the last parameter, let's ignore the flags and the user environment. The last parameter is the list of blocked fetches that we're going to fetch. And then we return a sync fetch, which contains an IO action. And this is defined down below here. So I'm not going to go into too much detail about how exactly we implement this. But as you can imagine, what you need to do is look at your list of blocked fetches here. So here's the list. We'll have to sort of collect those into batches. So we collect all of the get post content requests together so that we can issue those as a single query. So it's sort of done in two stages. First of all, we'll collect things into batches, and then we'll execute the batches down here. So I'll just sort of skim through the rest of the code. This bit's collecting stuff into batches. And this bit down here, we have a call to a thing called SQL multifetch, which I've defined down below, with a single query for each of these different request types. So this is the one that's selecting post content. And here we're sort of making a query with all of the IDs that we need to fetch post content for. Okay, and so as we saw before, this works, and this batches all those requests together. Yes?
I didn't get why the result bars operations were IO things. I can see that you need IO to execute a query, but why do you need IO to then unpack these things in the result?
It's a good question. So the alternative would be to return results somehow. Right, and the
Result of a block fetches maybe results.
so you would need to have a different kind of result. you would need to have something equivalent to block fetch which corresponded to a result, right? And you would need to return those, and then the framework would need to match up requests with results and pass them back to the right place. You could probably do that, yes. All right. So I've shown you how to make a data source. How do you sort of fit this together and actually run something from scratch? So there's a run Haxl operation. So this takes a thing called an env. And to make an env, we need to call initEnv. InitEnv takes a state store and the u thing, which we're not using, and returns an env. And to make a state store, well, we can construct a state store from the states for various data sources. So we saw how to construct the state for our blog data source. We have an operation that returns that state. So we can start with an empty state store, and then we can call state set with that state, with the empty state store, and we can get the state store that contains our data source state. And then we can pass that to initEnv, plug the pieces together, and eventually you can call run Haxl with your Haxl monad operation, and you can get the result at the end. So let's have a look at Haxl blog where we did that. So here's the run operation. So run takes a Haxl monad computation, which is defined here as gen Haxl using unit. So we initialize the data source, make our env from the state store that we get by using that database state, and then we can run Haxl. Okay, so we've seen all the pieces for a simple data source. But how does this batching work? So we saw that when you do multiple requests using mapm, they'll get batched together in a single query. But when does Haxl do the batching? Well, the simple answer is that when you use applicative, you get batching. So if you were to write something like this applicative expression here, where we're making a pair from the result of get post content 1 and get post content 2, those two would get batched together. If you use traverse, which is also defined in terms of applicative, this is like mapm for applicative, then you get batching. And nowadays, mapm is actually defined in terms of traverse for most data types. For lists, we're still trying to work out whether it has the same performance characteristics or not. But you can always use traverse instead of mapm and get the right behavior. And sequence A are the same sort of thing. Sequence A is the applicative version of sequence, and sequence will be defined in terms of sequence A. I think GHC 710 has that. But then maybe we don't want to use applicative syntax. Maybe we want to write do syntax like this, because it's in some ways simpler. You can just write a sequence of statements and not worry about having to make these large expressions. And you can name things. Okay, so let's have a look at some examples. So here's example 1 using applicative. And if we run example 1, we can see this managed to make a batched query. So we've got a select query for 2 posts. And if we run example 2, so example 2 was this one using do syntax, we just got 2 separate queries. Select for post 1, select for post 2, and then return the result. But what we can now do is turn on this clever thing called applicative do. And now if I run example 2, I get this nice batched query, which is exactly what I wanted. So what about if things get more complicated? So here's another example, example 3. So in example 3, I'm getting some post content, and now I've got another statement here which depends on the A that I got back from the first statement. And depending on the result of that, I'm doing some more fetching there. And finally, the last statement just gets another post content. And the return depends on all three of the results. So what's this going to do? Anybody want to guess? 3 requests, no batching I had. All right. So I've actually got 2 separate requests. In the first round, we got 1 and 2. In the second round, we got 3. So let's go back and look at that. So we managed to do 1 and 2, even though they were separate.
Did you change the order of the gets?
Well, yes. That's an assumption the framework is using. So I'll talk about some cases later on where side effects actually matter and the order matters. Okay, so we managed to do B after A. We managed to do C and A at the same time. So let's have a look at another example. So example 4. Yeah. Yes. Right. So I'll show you in a minute what the conversion to applicative actually looks like. So in example 4, we've got B that depends on A and D that depends on C. So anybody want to guess how many queries we get? Yeah, we should get 2. So yeah, we got C and A in the first round, and we got D and B in the second round. Okay, so applicative do translates do syntax into applicative as far as possible. So it looks for all the parallelism, and it tries to construct an applicative expression that embodies as much parallelism as it can find, as far as the data dependencies will allow. So if you use a do expression that has no data dependencies at all, what you end up with is an applicative expression that only needs an applicative constraint. Okay, so you can write do syntax and get something with an applicative constraint only. So you can now use do syntax with your applicatives. In our case, the monad is a monad as well as applicative. So we get to take advantage of applicative when we can, but then fall back to monad when we have to. So this example 3 that we saw, where we had a second statement that depended on the first statement, and the third statement depended on neither of them, what we end up getting is something like this. So we got, here's the function at the beginning. So this is the result. Depends on A, B, and C. And there are 2 arguments to this thing. So the first argument is going to return a pair of A and B. The second argument returns C. And the first argument is a sort of smaller do expression made from the first 2 statements, because we noticed that the second one depends on the first one. So we just made a smaller do statement here, do expression. And it returns the pair of A and B, because we noticed that A and B are required by this result here. Okay, and the second argument is just get post content 2. So I think this example is kind of interesting because when we first looked at doing applicative do, we thought it's as simple as just looking for sequences of statements that don't depend on each other. But actually it's more complicated than that. And in fact, to do an optimal job requires an exhaustive search, as far as we can tell. So GHC at the moment does not quite an optimal job. In most cases, doing a fairly good job is enough. So we found that sort of looking for the top level parallelism as much as possible, and then when we get down to sort of inner blocks, we look for ways to break the dependencies and then find more parallelism.
Question?
Yes?
Does that mean that the programmer in GHC can disagree on the type of the do?
No. Because the simple rule for types is You have to have no dependencies at all to get applicative. And that's a very simple rule. So the rule about how much parallelism you actually get is more complicated. So that's something I hope we'll be able to nail down in the future. But right now, GHC is sort of based on some heuristics. Question at the back? Yeah. Not at the moment. What I'd like to do is to have an optimal result. Yeah. That's another question. You get a type error, yes. Question? So here, had interleaving. Or perhaps you want to suggest another example. Okay, so good question. What if I do that? So now I've got B depends on A and D depends on C. So let's see what happens. So we got two queries as before. It is reordering things, yes. But it's reordering things within the constraint that if you were to flatten out the expression and evaluate it left to right, you get the same result. So it's reordering things only because our monad reorders things. A circular dependency using mdo. So mdo doesn't work with applicative do.
What if D fetched content of bus 3? Would it actually make it a separate query? Or?
Well, you're jumping ahead slightly, but I'll show you anyway. So we just got one fetch for 3 here. That's because of caching, which I'll come on to shortly. So again, that's an assumption. And you can control that assumption. But we're jumping ahead a bit. So just to sort of finish off applicative do, it's exactly what we needed for Haxl because we want to take advantage of parallelism as much as we can. And the idea is that people using our DSL can just write straightforward do syntax and they'll get parallel code automatically. And the status is it's currently in GHC master. It's going to be the next release, 8.0.1 of GHC. At Facebook, we sort of backported it. We're using it on top of 7.10.2. So if anybody else is interested in that, I can probably put up a branch or something. And you can use that. Just a data point. So our most common Haxl request in our application at Facebook does hundreds of data fetches, and they execute in less than 10 rounds, usually. So where a round is just a batch of fetching. So it's quite effective. Question? Yeah.
Could you do it in less than 10 rounds if you broke it out by hand?
No, those. So for the most part, those are real dependencies. There are cases where you have particularly complex interactions where the requirement for things to be flattened in a sort of equivalent left to right manner forces some dependencies where you wouldn't normally, you wouldn't have to have dependencies, but mostly those are real dependencies. Any more questions before I move on? All right, good. So caching. Haxl caches all the data fetches. So we saw earlier that requests have to be typable, hashable, and eq. That's because we're putting all these requests into a cache internally. You can actually see the contents of the cache. There's an operation called dump cache as Haskell, which returns a string in the monad. So let's see that. Okay. So run dump is going to be like run. So it's exactly like run up to here, and then we do another run Haxl here using dump cache as Haskell, and then we'll put the result, print the result. Okay, so here's our example. And the result of dump cache as Haskell is here. It's this load cache function, just a bit of Haskell syntax, and it contains a sequence of statements for each fetch that was made. And each statement is a call to something called cache request, passing the request that was issued and the result, where the result is either an exception or the result. So because this is a bit of Haskell, we can just go and cut and paste it. So let's just go and copy that, paste it into our code, and call it before we run the example. So it's a bit easier if I don't do that. So now we did exactly the same request as before with the same result, but now we didn't do any fetching in between. So there's no SQL query in the middle. And that's because we pre-populated the cache with all the results that we got from the first time we ran it. So this is a pretty neat trick that we call replaying. So you have to be a little bit careful because dump cache as Haskell uses show, and not all show instances are correct. So you have been warned, if you write a show instance that doesn't generate proper Haskell, it might cause problems for people who do this kind of thing. But it's really useful to be able to do this because you can just capture the cache, copy and paste it into your code, and now you've got a unit test for free. Right? You don't have to have the data source available at runtime, or the data source might even contain different data from when you originally ran it, but you can keep on running your unit test forever. And you can also sort of run it against dummy or mock data sources, which is very useful for sort of running local unit tests. Yes?
Is there a binary cache format or is it
Good question. We haven't done that yet. So it sort of throws up issues to do with compatibility, backwards compatibility and forwards compatibility and that sort of thing. The question was, is there a binary format? Can we binary serialize the cache? So yes, obviously you could do it, but then if you change the data types, your binary format isn't correct anymore. Yeah.
How is the cache contaminated again? When do you know that you need to do another query?
So the cache is stored in... So notice here that I ran the computation first of all, and then I did another run Haxl. So where is the cache coming from here to here? Well, it's stored in the env. So the env stores the cache. As soon as you throw away the env and start with a new env, you end up with a fresh cache. So yes, this is sort of a design point that we've thought quite hard about. When we're running this thing on requests in our application at Facebook, typically these requests are quite short-lived. They run for, at most a couple of seconds. And then we throw the cache away at the end. And being strict about having everything in the cache means that you have some nice properties. So it means that every time you see the same sub-expression somewhere in the program, it has the same result. As soon as you start throwing things away in the cache, you lose some of those properties. We did have one user that wanted to have a bounded cache size, so they implemented something. We haven't put that branch back into the master at the moment because we're not sure whether that's the right way to go. Any other questions? Yeah, one back.
Is there then some metadata associated with requests that tells you what are get from the hooks?
Very good question. If you don't mind, I'll defer that slightly. What about rights? I could be planting these people in the audience, it's great. So far we've only dealt with reads, okay? But it's obviously really useful to be able to batch and overlap writes and side-effecting operations as well. But we have to be really careful because, as we've seen, Haxl makes this assumption that everything you're doing is sort of reorderable, cacheable, and so forth. So let's see what happens. Let's see what happens if we make a simple logging data source where we're just going to write messages to standard output. So log data source is just another data source. It has a single operation called write log. Write log takes a string, standard boilerplate as before. There's no state in this case. And the implementation of our fetches is mapm do1, and do1 is defined as just put strlen of the string. And the result is just unit. Okay? And log example. Oh yeah, so just as a slight aside, this is how you make an instance of the monad with multiple data sources. So here I've used blog data source and log data source. And when I called initEnv, I've just made a state by using state set on both of these states. Okay, so what happens now if I use my log example? Okay, that works fine. Oops. So that doesn't work quite right. So probably what we wanted to do was to write x twice, but we got it once. So what we can do to fix that is to go back to our data source, and we can say, instead of data fetch, we'll say uncached request. And now that suppresses caching for that particular type of request. So that does what we want. Good question. What else can go wrong with writes? So what about when there are observable effects? So the effects with logging weren't observable, but what happens if we really need things to happen in a particular order? Well, let's make a data source for running external commands. I'll call this the command data source. So again, this is going to be fairly boilerplate. So this is the main operation, command, and it takes a program and some arguments. And it's going to call data fetch, and this is our request constructor, which is defined down below. Run command rec, takes the program, the arguments, and it returns an exit code. And we'll just throw an exception if the command failed. So what about the implementation of this thing? Okay, so this is slightly interesting. So I wanted to log some information about what commands are run and in what order. But I want to run these commands concurrently. So if I just print things out, all the messages will get interleaved. I won't be able to see what's going on. So I made a channel called logchan, and this is just going to carry messages. And this will enforce an ordering on the messages so that we can make sure the messages come out one by one. And that's the state for our data source. So now to initialize that state, we have to make a new channel. And we have to make a little thread that will read from that channel and put those messages to the standard output channel. So the only thing remaining is the implementation of fetch. So fetch is defined as build command fetch down here. And let's see, what am I doing? Well, I'm going to log some information about how long each command takes. So I'll need to capture the current time. And then for each of these, n is the command number. So I'm also going to log information about the number of a command within a sequence, within a batch. So n is the number of the command within the batch. And b is the request itself. And now I'm going to use the async library. So the async library is just something that lets you take an I/O action and run it asynchronously. So this returns an operation, well, it returns a value of type async, which I can wait for. So the result here is being waited for. And then fetch1 is the implementation that just runs the command. So we don't need to see what fetch1 does. All of the interesting stuff is just in this line here. So we're going to run all of the commands asynchronously at the same time, and then wait for all the results. So let's have a look at command example, which just implements the run operation as before. So let's just try okay, sleep for 1 second. Okay. So we did 3 sleep commands with different lengths. And we can see from the numbers on the left here, so this 1, 2, 3 indicates that all of these were executed at the same time, overlapped, and then they returned in order 1, 2, 3. Well, this was, because the logging is running in a separate thread, it sort of got interleaved a bit with the output. Okay. Let me do one more example here. So we can touch a file, and then we can remove the file again. That's fine. But these two have to be executed in the right order. So what happens if we say touch foo and then remove foo? Well, this went horribly wrong because, well, we got a batch of 2 commands here, and it did rm foo and touch foo at the same time, and then rm said cannot remove foo because it didn't exist. So how on earth did these 2 get batched together? This is kind of a surprise. Maybe I have applicative do on. Well, you have to run it a few times before it goes wrong. There you go. So it wasn't applicative do. So anybody know why this went wrong? Or why these were batched together? Nope. But I'm not using applicative.
Oh, sorry.
Well, you're not using the bind frame, right? Just deleting translation.
Right. So the answer is that when you use this operation, I've defined this operation to be the applicative thing, which is the obvious thing to do. But if you're not aware that the do syntax desugars into uses of the greater than operator, you might be slightly surprised when you get batching. So that's what happened. But there's a nice hack that you can get to avoid this. So if I say that, now I get them in the correct order. Well, so I know they're in the correct order, excuse me. I know they're in the correct order because I got 1 and then the result of 1 again. I didn't get 1 and 2. Okay, so the lesson here is that if you really want sequencing, you have to use the bind operator. Don't rely on the do syntax. Question?
That doesn't respect the idea of the monad that you define in such a way. You have to have a sequencing of
I'm not sure I understand that.
Do you think is this correct code?
If it obeys the laws, it's correct. Right?
It's behaving exactly as it should do. Yes. So the desugaring of do is defined to use this operator, and I've defined this operator to be that. So that's why we get batching. All right, so what else could we do with a data source that runs commands?
Tokens.
Well, I'm running out of time. I don't know. Okay, so this is going to be my final example. What do we do a lot that involves running multiple commands in parallel, where there's some non-trivial dependency graph between the commands that we run? Make, yeah. So basically a build system. So can we make a Haxl build system? And because I'm running out of time, I'm going to have to say yes and jump to the the demo. So let's see. So I have to build my build system first of all using make and bootstrap it. I've called it Haxl Shake for obvious reasons. And I'm just going to build some code using it. And that's it. So the code to do this is very simple. It's basically just a recursive program. We start by building the program. To build the program, we have to first work out the dependencies, which is Haskell dependencies. And Haskell dependencies builds a map from module to module representing dependencies. And then we just build each module. When we build each module, which is what this function Haskell module does. To build a Haskell module, we first build the Haskell modules for all of the things this module depends on, and then we can build the module. And because things are cached nicely, we don't do the same thing twice. And the framework takes care of making sure we get as much parallelism as we can while we're building, while we're traversing the dependency tree. So that's all I have to say. Thank you. Yes, that question has a rather complex answer, I suppose. Can we remove any of the I/O from the implementation here? And the answer is yes, but things get rather more complicated if you do that. So I must admit, I'm using I/O to sort of simplify the implementation in various ways. Does it make it harder to reason about? I don't know, because I haven't really put a lot of effort into trying to do it the other way. So we have had some interesting problems, particularly to do with exceptions. And what happens when exceptions are thrown in the middle of a data source, and how much of the computation should that should be preempted by that exception. And some of the sort of dark corners of the library were slightly unsafe with respect to what happened when exceptions get thrown and things sort of got into a bad state. So I suppose the answer is possibly. So, sure. So the question was, can we use any of the anti-abuse stuff that we're doing at Facebook for Wikipedia? And the answer is yes, but we haven't gone to the trouble of making our stuff generic so that we can open source it. And there's quite a lot of sort of Facebook-specific stuff in the application that we've built. So it would be quite a large effort. We've thought about it. And the answer is yes, but it would be a lot of work. At the back? Started off with a system in which we wanted to make the assumption that we could reorder things as much as possible. And then we wanted to do batching of writes and so forth. And we discovered that, well, we have to roll back some of these assumptions, some of the ways that we're using these assumptions. And the ways we're using the assumptions are caching and applicative do and the operation in monad that sequences things. So whether there's a nicer way to do that, I'm not sure, but that's sort of how we arrived at this situation.
So applicative do is it's quite a dangerous code transformation, to be honest.
Yes, so the property that it gives you is that the result is the same as long as you obey some laws, as long as your applicative instance has the right properties, namely that the angle bracket star operator is the same as app in the monad. It has to do the same thing. So I suppose you might say that some of the other things in the compiler are also dependent on certain properties, like the desugaring of the do syntax already depends on greater than having the same meaning as bind, right? So I think this happens in other places. I could probably come up with some more, but I can't think of any off the top of my head. But you're absolutely right. We should document very carefully what the properties are. And this already shows up in other places. If you have an applicative instance that doesn't quite do the right thing, then some other assumptions go wrong. Like we assume that mapm is the same as traverse most of the time. There isn't. It's a very good idea. And yes, I would love to build it and open source it.